All right, before I do the last question, I wanted to I had to rush through that one because I can only do 15 minutes at a time, and I was at the end. But make sure this follows. Like I said, we knew where we needed to end because that's the nice thing about induction. Like that, you know your goal at the end. So from here, I factored out the k plus 1 over 2. Now they both have a k plus 1 in it. This one has the over 2. This one did not. So to satisfy that, I just then I added a 2 to this expression. Because really, I factored out a 1/2 of this term. Well, if you divide this by 1/2, you're left with 2. And you could check, if you distribute this in, you're going to get these two terms. So I didn't make up any math. And then if I wanted to, I would write this is equal to this step. Obviously, k plus 1 minus 1 is the same thing as k. So that would give me to the last statement, which was the goal of my proof. I wanted to prove that k plus the sum of the first k plus 1 terms would be equal to this side. And remember, at the end, you would need to make some therefore statement of therefore for any. Let me move this over. You would say therefore. Whoa. Okay, failing. Here we go. Therefore, this formula is true for any n in the positive integers. That's what you would do to wrap up that problem. Okay, so now, last problem. Let's do this one together. So we want to use mathematical induction to prove this statement. So hopefully you're starting to get a feel for it. The other one, the one that we just did before, I can't remember if I said this in the other video, that one was a longer proof by induction problem and required a big mental jump. A lot of them don't take super long. You just have to believe in yourself and start. So here we go. So just like last time, I'm going to say step 1. So we're going to call this P of n, 1 squared plus 2 squared plus ... n squared is equal to this lovely thing. Okay, so start with P sub 1. So that would be 1 squared on the left-hand side. And the right-hand side would be 1/3 times 2 times 3/2 if you replace all the n's with 1. And that everything cancels, leaving 1. So left-hand side does indeed equal the right-hand side. Check. All right. Step 2. Assume. Just always write that word assume. That for some k, 1 squared plus 2 squared plus k squared is equal to, same statement, just with k's. Okay, so that's our assume statement. So now we're up to step 3. Okay, so we're trying to do the k plus 1th term. So the k plus 1th term is obviously 1 squared plus 2 squared plus k squared, and then the k plus 1th term squared. And remember, you are always using, you are always using the assumption statement in step 3. So here we go. So we know that this, from the assumption, is equal to this. So we're going to substitute that in. So we have 1/3 k, k plus 1, k plus 1/2. But then we still have this additional k plus 1 squared. Okay, so now what are we going to do? Are we going to multiply this all out? That doesn't sound super fun. Let's factor out a k plus 1. I haven't done this problem, obviously, so let's see what happens. We're going to factor out a 1/3 and a k plus 1. That's what we're going to do from both terms. So if we do that, the first term is left with k times k plus 1/2. And the second term, since I took out a 1/3, that leaves 3. And we're also left behind with 1 k plus 1. Okay. So we're getting there. May not look like it. Let's multiply the big parentheses out. And we have k squared plus a half k plus 3k plus 3. And we can combine that a little bit further. We have 1/3 k plus 1 times k squared plus 7/2 k plus 3. Okay, so I've kind of got an ugly quadratic in there. And often in the middle or at the very beginning, I sometimes just kind of write it to the side, where so we know that the p of k, so the sum of the first k squareds based off our assumption was equal to, our assumption says it's equal to this. So off to the side, usually when I'm doing a proof by induction problem, is I'll write, okay, well, what should the k plus 1th term end up being? So what should, in this case, what should the sum of the first k plus 1 squares end up if this holds true? Well, you basically just replace all the k's with k plus 1, so that would be k plus 1, then k plus 2, and then ran out of room there, k plus 3/2. So like all of these k's in the p of k turns into k plus 1s in the p of k plus 1. So hopefully that makes sense. So we have that off to the side. We could have done it at the beginning, but sometimes simple, and sometimes you get to a problem like this where you're like, okay, well, what the heck am I doing with this quadratic? Well, that's why we have this thing off to the side. It looks like I can just jump straight into that. Do we, let's see, we can check. Can we just call this k plus 2 times k plus 3/2? So let's see. Let's distribute these two in our head. 2 times 3/2 is indeed 3. K times 3/2 plus k times 2. 3/2 plus 4/2 is 7/2. Yeah, it worked. So we got there. So now we have finished step 3, and this is where we make our therefore statement. Therefore, 1 squared plus 2 squared plus blah, 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 plus n squared is equal to 1/3 n plus 1, n plus 1/2 for any n in the positive integers. And there you have it. That's the end of this proof by induction problem. So hopefully that kind of transferred in this video format. I would much rather have us been in person doing this lesson. This is the hardest lesson of the first unit usually. Remember, you can always reach out for questions. But give it a shot with your group, and I have a feeling that you'll kind of get a groove for it, and it won't be that bad. Okay, hope you all have a great day. Love y'all.